Okay, so we saw quote unquote the easy type. But let's try a more difficult one. Our test won't get anything tougher than this. And there is a project that's going to revolve around this type. So it's probably good that we at least see it. So without further ado, what if we don't have how many there are to begin with? So we just happen to know that after 4 days, we know that there certain bacteria had 215 cells in it, and after 6 days, there were 440 cells. Okay, so no starting point. We just kind of no beginning initial amount. We know that after these days, this many cells are present in this bacteria, and we're assuming exponential growth. We want to find an equation that we can use to predict how long it would take and how many there are after a certain amount of time. So what's the final? You find an equation, then predict how long it would take for the bacteria to quadruple in size. Quadruple the number of cells it contains. I'm actually going to show you guys how to do this problem two different ways. First of all, you hit pause and try your best. How far can you get? I suggest doing that a few times. Once I give you a nudge in the right direction, hit pause and take it further. How far can you go? Then come back and keep doing it that way. But I am going to show you guys two different ways to do this, and you can decide which way is more efficient and which way you like better. So let's start. I know that if I plug in a 6 for t, I would get 440 for y. All right, we're assuming that growth model, y equals ae to the kt power. We can always use that one. If I plug a 4 into t, there would be 215 bacteria. That would be y. So we're going to get two equations, and we're going to have two unknowns, right? That's a system of equations. It's been a while, but that's what it is. So there's the information. After 4 days, there's 215. After 6 days, there's 440. We don't have A. We don't have K. Those are our two unknowns. But there are the two equations we have, okay? So we can solve this. I won't say just like we did in Algebra 2, but we can solve this using a system of equations by using substitution. I can solve one of these equations for A and then substitute it into the other equation for A, and that would only leave us with one equation, one unknown, K, and then once we have K, we can back substitute and figure out what A is. All that vocabulary you should have heard before with systems of equations in Algebra 2, and maybe it's just been a while. So let's try it out. This is option 1, by the way. This is the first way to do this. Hopefully you're already thinking, well, maybe couldn't I have tried this? And we'll go into that. But let's finish option 1. If I solve this equation for A, this says A times e to the 4k power, I could divide that to the other side and call it A equals 215 divided by e to the 4k power. So that's where we're going to start off here with this page. I'm dividing that over, and I get what A is. Now I can go into my other equation. I can take A out, and I can substitute this mess in its place. There it is. 440 equals A e to the 6k power. Okay, we have a little bit, very little bit of exponent rules to apply here. I have e to the 6k on top, and I have e to the 4k on bottom. If we're ever dividing two exponentials with the same base, what should we do with their exponents? Subtract. E to the 6k over e to the 4k is actually e to the 2k. Nice. Now this is just like all the equations we've been solving so far in the book and taking our quiz on and all that. I need to solve for k. So I'm going to divide by 215. Then I'm going to take a natural log. If I take a natural log, that just cancels the e. And then I have k by itself by dividing by 2. So we're doing those three things. Divide by 215. Take the natural log. That will eliminate the e. And then finally divide by 2. If you jam that in your calculator, you get k, our little k constant for this moth problem, or bacteria problem, sorry. This bacteria problem is 0.358. So now we can go back, that's what this big arrow is about. I can back substitute now and go back and say, well, if I know k is 0.358, I can jam that into my calculator and I can figure out how many bacteria there were to start with. So I'll do that. I'll do 215 over e to the 4k power, just about equal to 51.3 cells in this bacteria to start with. That's it. We have A now. This. We have K now. This. The actual question was, once you found that, how long will it take for this specific bacteria to quadruple in size? So if I know that it starts with 51.3 cells, and I want it to quadruple in size, I'll just do 51.3 times 4, which is 205.2. So it's really like asking, how long will it take for there to be 205.2 cells in this bacteria? So I can go back to the equation I just made. I want the output to be 205.2. That's quadrupled in size. I can solve this equation just like we did. There'll be some natural logs involved, and hopefully you solve it and you get 3.9 days. About 3.9 days for this thing to quadruple in size. Okay? Let's look at option 2. Option 2, a lot of students prefer. So I showed you that way. That substitution, that works with all different types of exponential problems and sequences and things. So it's good to have that knowledge there. But there is an easier way to do it. The way we can do it is we can pretend that just because it's been 4 days since this thing has happened, since this bacteria has been growing, we can pretend that this day 4 is actually the initial amount. Pretend that thing is day 0. And in that case, there would be 215 cells to begin with. And then 2 days later, right, if this was day 4, if I go to day 6, if 2 days later, day 2, there are now 440 cells. So let's think about that for a second. We can say day 4 is actually day 0. That would make the initial amount 215. And then if we're talking day 6, from day 4 to day 6, 2 days have passed. So it's really like it's day 2, and I'm doing quotes here, day 2. So now we know the initial amount. We know how many days have passed. We know how many there are after those 2 days have passed, 440. We can use all that information and plug it into our exponential growth model, and we get 440 times equals 215e to the 2k power. But look, I'm bringing back that old one. When we went and did ours, we got the exact same thing, 440, 215e to the 2k, using substitution and using the exponent rules. We get the exact same equation. So the rest of this problem follows exactly the same way. Divide by 215, take a natural log, divide by 2, you'll get the same k value. We can go back, we can use the k value. The actual problem said how long to quadruple in size. Okay, well, A is our starting amount. So no matter what A is, like we don't even know A right now. I don't know how many there were to start with. I know what all this was to get our K value. But if whatever A is, to quadruple in size, I want it to be 4A. I want it to be 4 times as big. So our very next step to solving this would be to divide by A. And we don't need to know what A is. When I divide by A, those are going to cancel, and I'm just going to get 4 over here every time. Okay? If the actual problem said how many bacteria were there to start with, okay, then we run into some different problems where we're going to have to use our equation and plug in a negative value. We have to go back in time almost. That's pretty crazy. But because this one just asks how long to quadruple in size, I don't need to know the A value. I just know this is going to be 4 when all is said and done. 4. Then take the natural log, then divide, and we get the exact same answer either way. Okay? Here's your guys' stamp. Here are some logarithmic problems I would like you to try. Page 457, 1 through 8, 13 through 16, 25 through 35, odd, and then number 44. If I remember correctly, 44 mimics the way what the project will kind of look like, but I could be wrong. I'm old and forgetful. But try that stamp out. We might have to do like a video stamp sort of thing. Just be checking the what's out there page to figure out due dates. All right? Moving on.